Welcome everyone to the session on software reliability. I think in the midst of LLMs, generative AI and stuff, it's also critical to look at this reliability. And if you're there in the earlier session, right, we have got a lot of papers, a lot of work on reliability, a bit more than in LLM, which is interesting. So let's get started. I think we have the first paper by Atanu Kundu and team on data-driven falsification of cyber-physical system. So we have 4 short papers in this session. So I would request the authors, the presenters to take, let's say, 10 to 12 minutes. I'll alert you, and then we'll have 1 or 2 questions. Okay, over to you. Yeah, thanks.
Thank you. Good morning, everyone. Myself, Atanu Kundu. I am a research scholar at ICS Kolkata. Now I am going to present our research work, Data-Driven Falsification of Cyber Physical System. And this work is done under my PhD supervisor, Dr. Rajarshi. Okay. First, this is the talk outline. First, I will give you a brief introduction to the cyber physical system, and then I will discuss about our proposed falsification framework, and then we will talk about we will show some experiment result that we have found by our falsification framework, and at the end, the conclusion of this work. Okay. Cyber physical system is a system that contains both continuous and discrete dynamics. That means hybrid in nature. That's why cyber physical systems are sometimes called hybrid systems. Nowadays, such systems are everywhere, from smart building to autonomous vehicle to a medical device. Consider an example of such cyber physical system is the controller of an autonomous car, where the safety property is always maintain a certain distance, say 40-meter distance from the car ahead. So the system engineer needs to verify the controller before the actual deployment of the system in the real environment. So here safety is the topmost priority while developing such safety critical system. And generally safety properties are represented using reachability specification. And reachability specification is a pair of I, U, where I is the initial configuration and U is the unsafe configuration. And falsification is the process of finding a system behavior that actually finds a system behavior that violates the safety specification. Here in this work, we try to give a falsification framework that find counterexample from the such safety critical systems. In mathematically, counterexample is a tuple of xc, uc, tc that falsify the safety specification if the aim of xc, uc, tc intersect with the unsafe specification. Here, aim of xc, uc, tc is a state that CPS aim reaches starting from the initial configuration xc and with the influence of input signal uc after dwelling the tc amount of time in the CPS aim. Here in this presentation, I try to give you an algorithm that finds such type of counterexample from CPS systems. Okay, this is our proposed framework. Mainly, our proposed framework take only 2 inputs. One is the CPS M, and then one is the property specification phi, which is a pair of I, U. And our first step of our framework is to build a surrogate model from the corresponding CPS. And here we build actually a feed-forward neural network as a surrogate model. Then the surrogate model is evaluated to find a counter example. And our framework has option to choose either a NN verification algorithm or adversarial attacks algorithm to find the C from the surrogate model. And if a counter example is found, then we need to check it in the original CPS because we use the surrogate model to find the C. If not, then we add some constraint to the property specification to exclude such spurious counterexample from the C searching process. This is our main framework, and the main advantage of this framework is we have several options to choose which falsification algorithm we may want to use in this framework. There are several options like NN verification algorithm, adversarial attacks algorithms. Right. Okay. Here our first goal is to build a neural network model from the CPS system. All of we know data is more important to generate a neural network model. Uh, Here we generate the data set from the CPS by simulation using these three assumptions. One is the mass transition semantics. That means transition is taken as soon as the guard condition is satisfied. And we remove the non-determinism behavior from the CPS system. These two assumptions is for the hybrid automata models. And we also translate the time varying input signal to a piecewise constant input signal. This assumption is for the Simulink model, and these three assumptions restricts us to capture all the possible system behaviors from the CPS system. And this is the structure of our data set. The first three column shows the input features, and the last one is the corresponding output. Here, aim of x0, u1, 0 is the states that CPSM reaches starting from the initial state x0 with the influence of u after dwelling zero amount of time. Similarly, aim of x01, u1, j delta t is the state that CPSM reaches starting from the initial state x01 with the influence of u1 after dwelling j delta t amount of time in this type CPSM. In this way, we generate end simulation and store the data as a level data. Generally, we capture the all possible system behaviors from the CPMs at different time steps and stored as a level data to train the neural network model. Okay. Now we have a data set from the corresponding CPS, and we have to build a neural network model from this data set. So initially, we take a simple architecture of the FNN and that increase in complexity by adding hidden layer or add some neurons in that hidden layer until we got a satisfactory result. This is the architecture of a navigation benchmark, which is a well-known CPS. And we have applied the feature scaling techniques such as min-max scaling to normalize the input features. And we have used a fixed set of hyperparameter setting to train the neural network model, FNN model, like ReLU activation function, Adam optimizer, MAC as a loss function. And we have also used the early stopping algorithm, which actually monitors the validation loss in every epoch. If the validation loss is not improved in the patient's many parameter, since many epochs, then the training process is stopped and we got a neural network model. Okay. Okay, as we try to find the counterexample from a surrogate model, which is FNN, then we need to know what is the falsification problem of reachability specification, falsification problem of neural network model. Given a neural network model N and a reachability specification I, U, then the falsification problem is to find a input X belongs to I such that the output of the network X must belongs to the unsafe configuration I. That is very similar to the falsification of CPS system. Another definition is local robustness specification. Given a feed-forward neural network N and a input X, the network N is said to be locally robust with respect to the input X if the output of the network X and epsilon perturbated input of X is same. And this local robustness specification is required to apply the adversarial attacks algorithms on our framework. Okay, now we have successfully built the neural networks for the corresponding CPS, and now our framework find counterexample from the CPS system using several algorithms. Like we have option to choose these adversarial attacks algorithms like PGDF, GSM, BEAM, and similarly we have option to choose several NN verification algorithm like NN enum, reluplex, neurify. Suppose we have found a counterexample after using any one of this algorithm, then we need to verify this C in the original CPS because we have used the surrogate model to find this C and which is an approximation of the original CPS. That's why we need to validate it in the original CPS, and we validated it in the original CPS by simulating. For the hybrid automata models, we have used XFeed simulator, and for the Simulink model, we have used MATLAB. And if this C is not validated successfully, then this C is spurious and we have to eliminate from the C searching process. That's why we add some constant to the property specification and make is a modified property I prime, u, where I prime equals to I minus psi. Psi is the set of such spurious counter example that needs to be eliminated from the C searching process. Okay, and main observation in our framework is that our tool, our framework, which we call NNFL, is capable of generating new CE, which is not present in the datasheet. That is the main observation we have found in our framework. Okay, this is the some experiment results we have found. We have generally take two types of CPS systems. Some are hybrid automata models and some are Simulinks models. Here DOD is the degree of difficulty, which is the percentage of the falsifying trajectories in the in randomly simulated trajectory. That means DOD means lower the DOD, harder to falsify the falsification instances. And from this table, we can say that the adversarial attacks algorithm PGD is more powerful than the verification algorithm NNenum to find a counter example from the CPS system. Here, FR represent the falsification rate. We have tested each instances 10 times and find the FR. FR is the number of successful runs for which we found a counter example. Okay, this is another table. Here we compared our framework with the Falcon. Falcon is another falsification tool which takes only Simulink models. That's why we compared only. That's why we saw the result of only Simulink models. From this table, we can say that Falcon is capable of falsifying the instance set in very less amount time compared to our framework, but our framework has capable to falsify varieties of falsification instances. Like AGAS and AFC, our framework falsify with falsification rate 10, where Falcon cannot decide about the model safety. And this is the actual trajectory generated by our framework. This trajectory is generated from automatic ground collision avoidance systems, is a Simulink model, and this trajectory is generated from a navigation benchmark. Okay. Now we have demonstrated a falsification framework for the cyber physical system, and we have two types of cyber physical system. One is hybrid automata models, and another one is Simulink model. And our framework can also applicable to any type of CPS which can be simulated. And from this table, we can conclude that the adversarial attacks algorithm shows significant strength to the in compared to the NN verification algorithm to find a CE. We have several directions to extend this work. One is the GAN-based neural network model, which predicts more accurately. Another one is decision tree-based network, and MDP instead of neural network, because is handle the non-deterministic behavior in the CPS system. And our framework is implemented in NFL and available on GitLab. Okay, this is the two reference. First one is for the several adversarial attacks algorithm, and second one is the several NN verification algorithm. Okay, thank you. Thank you for your attention. Any questions?
Okay, let's thank your speaker. So any quick questions? As we're running out of time, like time for one quick question or comment. Okay, I have a very quick question. See, I was wondering, like, like you say the counter examples, right?
Yeah.
So when do you stop? Or, how many counter examples are enough?
Oh, no. We have stopped after getting one counter example.
Alright, so that's the question. Like,
Yeah,
what is the rationale for why you would stop at
our
one
algorithms try to find a counter example from the falsification algorithm. If found counter example, we check it in the original CPS.
Okay.
If this counter example is validated in the original CPS, then our algorithm stops. That is the model answer along with the counter example C.
Okay.
If this counter example is not validated, then we again recall the loop and try to find a new counter example.
Maybe it is interesting to explore other counter examples, and maybe there are some counter examples which could have more impact than others.
Yeah.
So maybe priority of the counter examples or something like that could also be interesting.
I was asking the same thing.
Oh, okay. So
how you ensure even whether maybe I would have missed it? How you ensure that model is well trained? And let's say if you see a counter example which is false,
yes,
then
then we add some constant. psi to the property
Yeah.
specification to eliminate such spurious counterexample.
Yeah, but my initial question is how you ensure that model is well trained. So
That means that is the question in machine learning model, how to build a neural network model.
Yeah.
That's some parameter we see some validation loss matrix, how the loss decrease. And another thing we considered that we have several falsification instances and try to run the neural network and get and check how much falsification rate we have found from this neural network. That's how I select the neural network.
Thanks.
Thanks again.